Hello everyone. So this presentation is about Java build tools. So the motivation for this talk is that although Java as a language is known to be extremely performant, very easy to learn, and have great support in IDEs, Java build tools like Maven or Gradle don't always live up to that expectation. And it's not just a problem for Java. Like even beyond Java, you look at Kotlin, you look at Scala, you look at like the JavaScript build tools. Like the complexity of build tools is almost universally a problem and a pain point and frustration within the programming ecosystem. So in this talk, we have four sections. First, we look at why these build tools are hard for users, but we'll also look at why the build tools are hard for implementers as well, which is why no one has come up and just made a better build tool to just replace all the old ones that we have trouble with. We look at one of my open source projects, which is called Mill, which aims to be a better build tool. And we look at some of the improvements that we can demonstrate over some of the more established and widely used build tools in the world. Lastly, we'll discuss the concept of object-oriented builds. So object-oriented builds is something that the Mill build tool is based upon. And it's something that I think is really important and that allows Mill to be much simpler and much easier to learn than many of the other build tools out in the world today. So just a bit about myself. I've been using Java since 2004. It's my first programming language. I've been doing open source projects since about 2012. My last job was at Databricks, so many of the projects are Scala on the JVM, since Databricks was a big Scala shop. But there's also a lot of other JVM and Java related technologies. My professional work is in developer tools, basically everything before a code goes to production. So setting up your dev environment, maybe a remote cloud-based dev environment, your build systems, your CI systems, maybe a multi-cloud CI system running on AWS and Azure and all that, and testing systems. So today, the topic of this talk is about build systems. So first, like, why are build tools hard for users? Looking at Java in particular, I think this boils down into three main categories. There's a performance, there's IDE support, and there's the ease of use or the programmability of these build tools that are commonly used with Java today. So one example here is that everyone talks about how the Go language or Go compiler is extremely fast, and is very fast, but no one talks about how the Java compiler is very fast, even though it is actually also very fast. And when you look at why, for example, look at the Netty code base. Netty is a popular asynchronous networking framework on the JVM. 500,000 lines of code, takes about 50 seconds to compile, 10x parallel on my laptop. I can show you this live. Let me just go here, copy this over to my terminal, go to my Netty folder. We won't wait for it. It'll take about 50 seconds and we'll come back to it in a moment. So if we look at this command, we are trying to skip as much as we can just to focus on compilation. But because of some intricacies within Maven's reactor framework, we have to use install rather than compile. It does have some overhead. So in order to try and isolate this compilation time, we can try and compile a single module, for example, netty common. In this case, I'm using Maven compile rather than install. No tests get run, no linters get run. I don't need to skip anything. And you see, it does still take a significant amount of time and compiles at about the same rate, about 5,000 to 6,000 lines per second. So this doesn't feel fast. Like people say, we compile stuff using Go, it's basically instant. But when you look at how fast the actual Java compiler takes, like if I just use Java-C from the command line rather than using Maven, it's 3x faster than using Maven to compile the same code with the same source files and the same third-party dependencies. So I just use Java-C. It's a bit of a long Java-C command. I shrunk the class path so it doesn't take up the whole screen. And you'll see it takes 1.5 seconds instead of 4.5 seconds. And those of you who have been using Java for a long time would know that running Java-C code from the command line is like the worst possible performance you could ever get out of the Java compiler. And that's because Java compiler is a Java application written in Java, running on the JVM. Like any other Java application, it suffers from slow startups, but after it runs for some period of time, the JIT compiler kicks in, the JVM warms up, and the performance gets a lot better. And by running code from the command line, you never get the fast performance, and all you get is a slow startup. So to try and measure that, we can run Java C in memory. So I'm going to show you this bench.java file I wrote that does that. It's not very complicated. It just runs Java C in a while loop. And instead of taking 1.5 seconds, it runs 5 times faster. So now we're compiling 29,000 lines of code in 0.3 seconds. That's about 100,000 lines a second. So if this was the experience that people had got developing in Java, that their code compiles in like a fraction of a second, I'm sure people would have a lot more positive view on the Java developer experience and Java programming stack than they do now, where it takes many seconds to compile even a relatively small and simple module. So just to show you this live, earlier we saw that I kicked off Maven clean compile or Maven clean install everything on 10 cores on my laptop on the netty code base. It took about 1 minute, so more or less the 50 seconds that we saw on the slide. If I run Maven clean compile on a single module, which is the netty common module, so that's a clean. If you run the compile, it should take about 4.5 seconds. Now it took 5.3, more or less there. If I run Java C without Maven, as you see, the class path is a bit long. You're not going to actually type this out yourself, but just as an illustrative example of how fast things could be. It takes 1.45 seconds instead of 5 point something seconds. And I have this bench.java script I mentioned earlier. So bench.java, all it is a single file Java program that has a while true loop and runs the Java compiler programmatically over and over using basically the same flags we saw in the terminal. So the goal of this is just keep the Java compiler warm, keep the Java process hot in memory so it has a chance to get JIT compiled and optimized and performant. So if I run this Java bench.java here from the command line, you see the first run probably isn't particularly fast, but over time it gets faster and faster, and this duration you see here where my mouse is drops. This is what's happening as your JIT compiler kicks in and progressively optimizes the Java application, in this case the Java application being the Java compiler. And after a few runs, we're looking at somewhere around 300 milliseconds to compile 30,000 lines of code, and right now, in this case, about 80,000 lines a second. So slightly slower than the numbers we saw on the slide, but more or less there. So compilation times aren't the only thing that takes time in your developer workflow, but this is just one of the many ways in which your build tool takes what's actually a very fast underlying Java toolchain and wraps it with enough overhead that it kind of feels a bit sluggish and clunky. So rather than taking 0.3 seconds, you're now taking 4.5 seconds. And you can imagine if we had this 100K lines of second compilation performance to compile a whole netty code base, it should be really snappy, even for such a huge 500,000 line system. So that's one of the ways where the build tool performance kind of lags behind your Java runtime performance. It makes it feel not quite as performant as you would expect from a Java system. Next, let's talk about IDE support. So every build tool in Java has IDE support. Java itself is known for having excellent IDEs, from NetBeans to Eclipse to IntelliJ is more popular nowadays. But the build tool IDE support doesn't always quite match up to that expectation. So if I pull down an example, let's see which one I want. I think I want this one. So over here, I have the Mockito code base open in my editor. Mockito is a popular open source unit testing mocking library, and it's built using Gradle, using the Groovy DSL. So you see the Gradle script I have open, which is a Gradle config for the error-prone submodule. It does have syntax highlighting and some like jump to definition and stuff. But when you actually try to dig a bit deeper, you'll find that the IDE like navigation and analysis is pretty disappointing. Like I can jump to get JVM args, I get this getter and setter, but I don't really see like what was the value before I set it, and after I set it, where does the value get used later. I kind of just get the signature, I get the name. If you set up the sources, you can get the java.doc comment, but that's it, right? Like in any Java application, you expect to get much more than that in your jump to definition. And it's not just one thing, like anything you jump to in your Gradle script, you can't get this getter and setter and nothing else. So this is in contrast to actual Java code. Like if I open up any Java file within the Mockito code base, I can jump to any of these uh, any of these methods, any of these classes, and you expect to find something useful, not just a signature, not just a name, not just a document, but implementation. What does it do? And you can recursively explore this program. So even if the signature is not helpful, even if the document is missing, even if the name is misleading, you can always find your way around and figure out what your program is actually doing. That's something that you cannot do when you're trying to use your IDE to explore your build tool. Why is that the case? This is the same IDE running a project written in actually the same language. The Gradle script may be groovy, but the underlying code is all in Java as well. And the answer to that is the basic problem with many tools like Gradle is that the build tool is basically built around all these global mutable variables like JVM args and compiler args. And just because you wrap them in a getter or setter doesn't make them any less global or any less mutable. And IDs are not good at navigating around global mutable variables. In fact, humans are also not good at figuring out how to work with global mutable variables. And when you jump to definition in a for a global mutable variable, what does the definition give you? You get the name, you get the type signature, maybe you get a document, but you get no information about where the value in that variable came from or where the value in the variable is going to be used later. Anyone could be writing to this, anyone could be reading from this, and you have no idea. And that's exactly the experience you get trying to navigate around Gradle in your IDE, because Gradle is fundamentally built around these global immutable variables. And therefore, navigation around your build tool in your IDE is pretty inferior to what you expect when compared to navigating around your application code, which is typically built not around global variables, but around classes, methods, method calls, and overrides. All of which your IDE are very good at understanding and navigating. So that's the problem with IDE support. And we looked at the Gradle Groovy DSL. The Kotlin DSL, despite being statically typed, has similar problems. Static typing doesn't solve the problem of global mutable variables. And the Maven XML has a similar problem as well, in that you can often jump to an XML schema definition in your pom.xml file. And again, it will tell you the name, documentation string, and signature, but won't tell you like where does this value actually get used, or what was the value before I came and overrode it or set it. The last thing we're going to talk about here is the idea of programmability. So every build tool has plugins, every build tool has built-in functionality. At some point, the built-ins are not enough, the plugins maybe don't do quite what you want, and you need to customize it yourself. That's a tale as old as time. For example, let's use this strawman requirement that I want to save the project line count as a line count.txt resource file. So this is a bit contrived, this is a bit arbitrary, but it's representative of the many arbitrary things that you actually have to do in any real project. Like the Netty project we saw earlier, you have to compile C code using GCC or Clang and link it together using one of the linkers available on Linux, Mac, and Windows. The Mockito code base we saw earlier has to do bytecode and class file mangling in order to make its mocks work. So every project typically needs to do something special because everyone's business and everyone's system has some unique things to it. That's why they're not just using an off-the-shelf one. And as a representative example, let's just say I want to save the project line count. So doing this in Maven or Gradle is not rocket science, but it can be surprisingly tricky. So here's an implementation using the Maven exec plugin. And it calls out to bash or shell to do stuff. So there's some limitation around Windows. This doesn't work on Windows. You may have to do something else on Windows. But apart from Windows, there's another bug in it that I'm guessing none of you will be able to spot. So if someone submits this code to you for code review, some junior engineer says, hey, I wrote this, or ChatGPT wrote it for me, like, I think it should work. Let's put it in our main build, or let's put it in our plugin. And you look at this, and you won't be able to spot the bug. In this case, the bug is we forgot to escape our ampersands. So, this is not just bash or shell, this is bash shell embedded in XML. XML demands that you escape your ampersands at ampersand amp, semicolon. So it's surprisingly tricky just to get this right, even though this is really the most simplest hello world build customization you could ever hope for. And this is one way of doing this in Maven. There are other ways, and all of these ways have their own trickiness. Like bash scripts outside of Maven are tricky, and scripts have their own problem and difficulty in writing them. Custom Maven plugins, the plugin API in Mojos and stuff is not particularly well documented and not commonly used. And so even a simple thing can be surprisingly difficult and error prone. Gradle has a different set of trade-offs. Gradle, in this case, using a Kotlin DSL, runs on the JVM. You don't need to worry about Windows. You don't need to worry about bash or XML escaping peculiarities. But there's a bunch of other things that you need to worry about, like making sure your depends-ons and input files and output files and do last, or do you actually want to do first, lined up correctly. And again, there's a bug in this. In this case, the bug won't affect correctness, but now this bug will non-deterministically slow your program down, your build system down, depending which file you touch. And here the bug is we are listing the files in source main Java, but we set a dependency on the folder source main. So we actually wanted to set a dependency on source main Java as well. And by setting a dependency on source main, that means that if someone touches your source main templates, your source main config, your source main resources folder, it will cause this task to unnecessarily recompute, even though the output could not possibly have changed. So this kind of problems or difficulty finding these bugs in your Gradle or Maven code is like a microcosm of why people don't like configuring their builds. Like, it is so error prone. Simple things can have such subtle bugs. These bugs can be non-deterministic. These bugs can be performance bugs. And in the end, these bugs will slip through into your build and end up in your main branch. It will cause slowness, flakiness in your build that no one can figure out what's happening. And even if you don't customize it yourself, you might have the plugin authors who make the plugins that you use in your build may have the same bugs. Your plugin authors are human as well. And that results in plugins being slow, flaky, or plugins not behaving well when they interact with each other, which is, I'm sure, is a common experience all of you have gone through, trying to pull plugins into your build and having things not quite work as you'd expect. So that's why build tools are hard for users. It's a performance, ID support, and programmability. Again, Java is well known to be great at all of these things, but Java build tools somehow don't quite live up to that reputation. So if build tools are so hard for users, why doesn't someone just go and make a better build tool? There's millions of Java developers out there. Everyone encounters some problems at some point in their life cycle developing Java applications. Why hasn't it already been fixed? And the answer to that is that build tools aren't just hard for users, like people who are using the build to set up their own application, but build tools are hard for the people designing the build tool as well, or implementing the build tool. So, every build tool starts off very simple. For example, JBang starts off with a few key value pairs, and that's it. Really simple. But at some point, your key value pairs get numerous, they get a bit messy, and maybe you want to put them into some kind of like hierarchy rather than just a flat list. So this is a GitHub Actions config. GitHub Actions can be thought of as a build tool of sorts. And you can see that by putting things into a YAML tree, it becomes a bit neater than having everything in one huge flat list that would otherwise be required. But after you look at this YAML tree a while and work with this YAML tree, you'll realize that we're not actually just purely looking at a tree structure. We have these variables that we are declaring, passing in, and referencing somewhere else. We are declaring a build here, and we're using the build here, and we're declaring this shared workflow here, and we're using it here and here. So although GitHub Actions looks like a tree, what you actually care about is this graph structure that comes out from your build. And like when you make a change in GitHub Actions, what could possibly break? Well, you look at the graph. When you run in GitHub Actions, what runs in parallel? You look at the graph. When you have to propagate some variable throughout your GitHub Actions so other parts of the config can use it, again, you're looking at a graph. So the last thing to discuss here is that beyond graphs, you often need to template your build as well. So this is an example from Maven 4. The newer version of Maven has a mix-in functionality where you can mix in multiple POMs by referencing the mix-in POM using its coordinates. And by mixing in multiple of them, you can end up kind of fleshing out your main pom.xml to have all the functionality you need. And this is necessary because you don't want to copy paste everything throughout your build. You may have 100 pom.xmls, and if you copy paste things between them, they are sure to fall out of sync, they are sure to get inconsistent, and it's very hard to maintain this type of copy paste build config. So you end up with some kind of inheritance model. In the case of Maven 3, you have single inheritance with parent POMs. In case of Maven 4, you have multiple inheritance even with mix-ins. Referencing these mix-in POMs. So what I've been getting at with this long spiel about build tool complexity is that build tools are fundamentally graph computation engines. Every build tool needs to define templated graph computations, like what we have here, where we have a 3-module example build graph of 3 modules, each of which has assembly and compile and class path and so on. And not just define it as a build tool, but the build tool needs to let you, as the end user, define a templated graph computation. So it needs to have a graph because you need to parallelize and order things, and you need the graph for that. You need the computations because jars and class files don't create themselves. Somebody in Bash or in C or in Java or in Kotlin or some on Groovy needs to specify how your jars and class files and other things are being created. And it needs to be templated because the different submodules within your build are often very similar, even if they're not quite the same. So you need to have some way of templating them to reuse the commonality while still being able to configure the unique configuration for each submodule. So there are lots of ways to do this. We saw how GitHub Actions does it, where the graph is defined with needs keys, computations are the bash snippets, and templating is done by these curly braces. Some build tools hide this in plugins. Again, this doesn't really solve the problem. If it's difficult to define these templated graph computations, your plugin authors will have difficulty too. And that's why your plugins end up buggy, flaky, or unmaintained, and plugin authors just find it's too much work, too much effort to keep these things up to date. And this makes build tools complex. So any build tool will need to answer a whole lot of questions related to templated graph computations. Things like, how do you define tasks? How do you run them from the CLI? What needs to run in what order? How do we define what a task actually does? How do we pass data between each other? And if you look at any build config, for example, the Gradle Kotlin line count build config we saw earlier, you'll see that the complexity of the Gradle build is not just for fun, but it's actually to answer all these questions that any build tool needs you to answer. So that's why build tools are hard for implementers. Like, it's not just, the build tool author will overcomplicated things by making it complicated. It's that everyone wants it to be simple and starts off with some really simple schema. But because the build tools do complicated things, these templated graph computations, so the build tool API that the user faces, or configuration language, or CLI, needs to let the user manage these templated graph computations, and that is fundamentally a very complicated problem. So in the next section of this talk, we'll talk about Mill, which is one of my open source projects, and it tries to improve upon this status quo, and I'll leave it to you to judge for yourself whether you think it's successful. So Mill is an open source build tool targeting all the JVM languages: Java, Kotlin, Scala. There's an open pull request, someone's trying to add Groovy support. And the build files look like this. So the Mill build files are written with Scala syntax, so slightly different from the Kotlin syntax you may see in Groovy, or in Gradle, or the Groovy syntax, but hopefully not too alien. So like the packages, imports, extends, class, those are all things you understand. Object defines a singleton object, kind of just a nicer syntax for an anonymous instance of this class. And I can override things using the methods which are defined using DEF. So again, slightly different from Kotlin's FUN or Java's public static method name, but hopefully you can kind of see what this does. I have an object which extends a class, I override this method. I have a static nested object which extends one class and one interface. In Mill, they're called traits. So Mill's not a huge project like Maven or Gradle. It's not 20 years battle tested, but it does have a small community around it. Maintainers, committers, contributors. I know people at Disney and Netflix and Sci-Fi have been using Mill in their projects. Not all their projects, but some of them. So people have been trying it out at least. You can use Mill like from the command line as so, like /mill, foo.compile, foo.run, foo.test, foo.assembly, and so on. So this is what Mill does. That's the same as every other build tool. And I think what's more interesting is where Mill tries to improve upon the existing build tools. And we'll go through the three areas of performance, IDE support, and programmability that we discussed earlier. First, performance. So to compare performance, you need the same build in two different build tools for the same project. And naturally, most projects out there don't maintain multiple build systems for fun. So we had to make our own benchmark. So what we did is we took the Netty code base that we discussed earlier. It's normally built using Maven, 50 sub-projects, quite a big code base. And we ported it to Mill just as a proof of concept. So it's not like a full port. You're not actually using this for the published version. But it's just a demo of, we got it ported to Mill, we got all the test passing, got all the code compiling, just so we can see what it's like using Mill versus Maven in an apples to apples scenario. Once we did the port, we did some rough benchmarks. In this case, again, it's just a compilation benchmarks, but you can do benchmarks for testing and other things as well. And you see that in many cases, doing things using Mill is doing the exact same thing using Mill, just happens to be like 4 to 6x faster than using Maven. Earlier we saw it took about 50 to 60 seconds to parallel clean compile the whole code base using Maven. I can show you how long it takes using Mill. So here's my netty code base in my terminal. I can do mill clean and time mill wildcard.compile. Mill is a JVM map again, so the first execution may be slightly slower, but hopefully it'll warm up over time and we'll see it get faster. So the first run of a clean compile, rather than taking 60 seconds, it looks like it's going to take around like maybe 15 seconds. And subsequent runs will get faster as Mill keeps the JVM warm in memory, so that even if you're running separate commands from the command line, can benefit from the JVM's JIT optimization and other performance improvements. So yeah, it took about 10 seconds, more or less what we saw here on the slide. Incremental compiles and other things. Basically for the clean compiles, Mill is generally about 4 to 6x faster, and for incremental compiles it's even more, because Maven doesn't have a very smart way of selectively compiling a Java file. So when you make a change and add a print line, Maven just compile everything and all downstream modules, whereas Mill is able to detect in like 0.2 seconds that we only need to compile one file and can exit and proceed with further work. So we did the same benchmarks using Gradle. Gradle is somewhat faster than Maven. I don't know if any of you have read the Spring Boot report where the Spring Boot guys migrated from Maven to Gradle, and it's much faster. In this benchmark, instead of being 4 to 6x faster than Maven, Mill ends up being about 3 to 4x faster than Gradle. So it's not as dramatic a speed up, but it's still substantial. So compilation performance is not everything. Some other interesting areas where Mill is quite good is, for example, handling large monorepos. So Maven, Gradle, other build tools like SBT often have problems where when you have more than, say, 100 subprojects or 200 subprojects, you end up having these long configuration or initialization times. Whereas Mill works quite well with even like 500 subprojects in this example. If you do a cache compile on this 500 subprojects, it takes about 2 seconds. So that's just representative of how much build tool overhead Mill has for such a big code base, about 2 seconds of overhead. If there's no actual work to be done. And Mill also supports multiple languages, even things like Android or Python or TypeScript. So if you have a big code base with multiple kind of a heterogeneous tech stack, you can manage it using Mill, where it's quite difficult to manage these heterogeneous monorepos using Maven or Gradle. Mill profiles everything automatically for you. So if you run a Mill command, you automatically get a Chrome profile you can load into your browser and see where the time went. So for example, if I go back to my netty code base, I just ran a clean compile all here, right? And if I open it up in my IDE, let me pull that up, you'll see that I have this Mill Chrome profile file that gets generated containing metadata about what tasks took how much time. So you're not meant to read this yourself, but what you can do is you can open up Chrome, go to Chrome://tracing, which is a web app that everyone already has in the Chrome browser. I'm not sure if you knew. And you can drop this in and see exactly where those 10 seconds went when I ran my Mill clean compile all. So you can see where the Mill command was well utilizing all the CPUs. You can see where it started getting bottlenecked. It got bottlenecked on common compile. It got bottlenecked on microbench compile. You can see how long any of these things took. Like common compile took a wall duration of 1,851 milliseconds. And even if you didn't know anything about Mill, and even if you didn't know anything about the netty code base, you already may have some ideas of things that could be improved if you wanted to speed up the clean compile. Like for example, maybe microbench could be broken up into separate submodules so that they could run in parallel rather than having this long compile single module holding up the entire command. Now I'm not saying you have to do this, but if you wanted to do this because you're wondering why your command was taking so long, Mill makes it very easy for you to figure out why is your command taking so long so you can do something about it. Apart from the Chrome profile, selective testing is interesting. So if you have a pull request that touches, say, one file in one submodule, Mill makes it very easy to check out your main branch, take a snapshot on the main branch, check out your pull request branch and ask Mill, what tests do I need to run that are in modules that are downstream of this code change? And Mill can let you actually run them so that you only need to run the tests relevant to the code change, and you don't need to run tests, for example, in upstream modules which could not possibly be affected, or in parallel modules that again could not possibly be affected by this code change. So this is very useful in larger code bases where you're usually not touching the whole code base at once. And by selectively running the tests of the modules that are relevant to your pull request, can save a lot of time waiting and a lot of money spent on GitHub Actions workers or other CI systems. So that's a performance angle for Mill. As a baseline, it's just faster than Maven or Gradle. It's not as fast as Java C should be. Like Java C is 15 times faster than Maven. Mill is like maybe 5 times faster than Maven, but it's significantly faster, and you're trying to drive that number up over time. And has support for a lot of interesting features like large code bases in many submodules, performance profiling, selective testing. All of these things are things you could theoretically set up for a Maven or Gradle builds, but it's sufficiently inconvenient you probably won't. Whereas the Mill is really easy to set up, and so you can get these benefits quite easily. Next thing to talk about is IDE support. And I'm going to say that Mill has better IDE support in IntelliJ and VS Code than Maven or Gradle. And let me show you what that means. So over here on the left, I have the Mockito build for Gradle. The Gradle build for Mockito. And I'm going to pull up the Mill build for Mockito to put on the right. So let me just pull up the equivalent file. It's error prone, object error prone. Here we are. So here's on the right is the Mockito error prone submodules Mill build, and on the left is the Mockito error prone submodule Gradle build. First thing you realize is that they look very similar, and that kind of makes sense because let me get rid of this profile. Because the Mockito error prone submodule requires these flags to compile, requires these flags to run, requires these dependencies, and Mill doesn't work magic. Mill needs to configure the same things as Gradle, Maven based, or any other build tool would need to. But where things are different is that where Gradle is configured using global mutable variables, which means when you jump to them, you get nothing useful. On the right here, you can see Mill is configured using overrides. So def in Mill Scala syntax is for defining a method. This method fork args overrides an existing method. You can see IntelliJ is able to identify the override, can bring me to the overridden method. You can show me the type signature, the comment, say the name, same as what we saw on Gradle, but also the previous value, in this case an empty sequence. So this syntax again is Scala syntax, so it might be slightly different from the Kotlin you may be used to in Gradle or the Groovy, but hopefully you can more or less guess what it does and it's not too strange. And once I have this method, def fork args, I can just look who's calling it. So fork args gets used by runner gets used by run background task, and run fork task gets used in run. So unlike in Gradle, where you jump to something, you just hit a wall, you get a global mutable variable here with no idea where it's used or where the value came from. In Mill, I can take my fork args and trace it through my build graph step by step, just following the IDE's find usages that we saw earlier, and see how fork args ends up being used in run. And I can go the other way as well. So I can go upstream from final main class, which has no documentation, but in Mill that's not a blocker. The no documentation, but I have the implementation. You can see mostly delegates this final main class opt thing and just fails if the value is not what we want. So I can jump to final main class opt, which again has no documentation, but I have the implementation. I can see it calls main class, which is any explicitly specified main classes. If there is one of these, it uses it. If there's none, it calls all local main classes. This is any main classes detected, and we use class graph to look for class files containing public static void main methods. And if there's no detected main classes, we have an error message. If there's exactly one, we use it. If there's multiple, we also have an error message saying that, oh, there are multiple main classes, we're not sure which one you want. Please explicitly specify it by overriding the relevant method. So what's interesting here is that Mill's IDE experience is exactly the IDE experience you get every day navigating around your Java, Kotlin, or Scala code base in IntelliJ, in Eclipse, in VS Code, in anything. Even if a method does not have documentation, even if you're not sure what the method does or method's buggy, that is not a blocker. You can just jump to definition, find usages, jump to definition again, and figure out how the method works and how it fits into the rest of the code base without ever getting blocked. So that's what you have in Mill, where I showed you how you can navigate from my initial fork args into the Mill build graph and see how fork args interacts with run, interacts with final main class, interacts with main class and all local main classes. And you can all do all of this in the comfort of your IDE and without being beholden to just like what's available in the documentation or what ChatGPT or Gemini or Stack Overflow are able to provide you in code snippets to copy paste. So that's the IDE support angle, where I think Mill is actually really cool in its IDE support. It's much nicer to navigate around your Mill build than it is to navigate around a Maven build or a Gradle build or a Bazel build in your IDE. And it feels much more familiar to anyone who's ever been using their IDE to navigate around the JVM language code base like Java, Scala, or Kotlin. Lastly, let's talk about programmability. So most build tools require extensions to be published as plugins. This is great because often there are plugins that do what you want. This also has downsides. Sometimes the plugins don't do what you want. Sometimes the plugins are unmaintained, haven't been updated for 5 years ago on GitHub. Sometimes the plugins are buggy or difficult to use, or maybe they interact badly with each other. And sometimes you often just have to do something yourself. Like you can't always rely on plugins. Sometimes the plugins are not suitable for what's actually quite a unique use case within your business or organization. So in Mill, what Mill does differently is that although Mill does have plugins and you use plugins, you don't need to use plugins. You can often just write code and use libraries to do things yourself. And let me show this to you. So give me a moment to set up my IDE's windows. So move these away, move these back. So and go here in my terminal, custom Java. So over here on the right, you have the Mill build for the minimal Java application. I have some imports. I have an object foo extends Java module. This means the foo subfolder is a Java module, and there's no config. So Mill kind of inherits the convention over configuration concept from Maven and Gradle. And if you don't have anything special in your module, well, there's nothing for you to configure. But let's say we did have something special. Let's say we wanted to save the line count of this project's source files and put in a resource file to use at runtime. How would you do that? So in Mill, custom tasks are just methods. Mill uses Scala syntax, so methods are just defined using def, maybe def line count equals task. And within this method, I can call other methods. For example, I can call one of the foo source methods. And if you're not sure which one to call, IntelliJ is happy to help you and give you your documentation. So here I can say all source files is all individual source files fed into a Java compiler. I can use that. I call it, I map it. So each file, I read the lines of that file path, get the size of those lines, and sum them up. And that's all I need to do to define a custom task using Mill. I can now do Mill show foo.line_count. You can see it prints once the build loads. It prints 17. You can see this is the number of lines of code in this small example application. I can do Mill inspect foo.line_count. See that just by defining a method with a dot comment, we become a task where the inputs get captured for you to use at command line. The dot comment gets captured to use at command line. We have a file name, line number, so you can find this thing later if it's in a big build file. I'm not sure where it is. So that's all we need to do to define a line count task, but we have yet to write it as a resource file. So in Mill, everything's a method, and that includes resources. So if you want to customize a method in any JVM language, you use overrides. So I can do override def resources. Again, you're not sure which one you want to override. You can just ask IntelliJ or VS Code, they'll help you. In this case, I want this normal resource method. I'm going to keep the super resources, but I'm going to write to this task.destination folder that I'll discuss in a moment, my line count as a string. Let's put that like that. I'm going to append this to my resource path. So this is a syntax for appending to a sequence in Mill. So what is task.destination folder? So if I do Mill show foo.resources, maybe make this a bit smaller so it doesn't wrap. You can see that in addition to this foo/resources folder, which is the original resources folder, in this override we have to refer to it as super, we also have out foo resources.dest, which is this task.destination folder. So the point of this is that in every build tool, the file system is the world's biggest global mutable variable. Anyone can read to anywhere on it, from anywhere on it, write to anywhere on it. You can stomp over each other. Different plugins can stomp over each other's files. You have race conditions when things run in parallel and are trying to write to the same files or folders on disk. In general, this huge global mutable file system becomes a big mess. So with Mill, we said that, well, we don't want the global mutable file system. Instead, every task gets a folder that it can write to and everyone else can only read from. So the foo.resources task gets a foo out/foo/resources.dest folder. Foo.compile will get compile.dest. Foo.assembly will get assembly.dest, and so on. So rather than having a global mutable file system, we get a locally mutable file system, but it's globally read-only. That makes it much easier to manage the build in a big project. It really removes this whole file system problem where different plugins or different tasks may be interfering with each other on disk. And now if I do mill foo.run, you'll see that my application code is able to load my line count at runtime that was generated at build time in the build task and print it out. So let's take this one step further. Rather than just printing out the line count, let's say I wanted to use a third-party library in my build customizations. Let's say I wanted to print out the line count as a HTML file rather than as a text file. So this is kind of contrived and arbitrary, but it's again representative of the many arbitrary things you may need to do in your build. Like many of your build tasks would need third-party libraries from Maven Central. Maybe your linter is from Maven Central, or your packaging executables from Maven Central, or some helper library you need is from Maven Central. So to illustrate this, let's say I want to import TimeLeaf in my build and use it to render some HTML. So Mill doesn't have TimeLeaf built in. It's not a web framework. It's a build system. If I try to run this in the terminal, it yells at me, and my IDE is yelling at me as well. So that doesn't work. What Mill that does let you do is it lets you have this magic comment syntax, similar to the JBang syntax we saw earlier, where I can have a comment at the top of the file that says, this build requires org.timeleaf 3.1.1.release. So this is similar to JBang, just using YAML instead of its own custom key value pair syntax. And once I have this in and I reload my build in IntelliJ, hopefully this works. If this doesn't work, I may have to close the editor and restart it. Let me do that. The ID support's not perfect yet. As I mentioned earlier, Mill's a much smaller project than Maven or Gradle, so there are some bugs in the ID support still. But let me reopen this and hopefully it will work this time. Okay, so it's importing. Okay, and we're done. So now I think we are loaded and we have TimeLeaf available in our build for us to use. So now that TimeLeaf is available, I can see it in my libraries list. I can autocomplete it in my IDE. I can import, for example, template engine. I can define a new task, say HTML snippet, that calls TimeLeaf to say var context equals new context, context.set variable, line count to line count as return value, new template engine dot process, and I'm going to copy the template from the slide because it's the TimeLeaf syntax can be a bit finicky to write. So process this context. Now if I do mill show foo.html snippet, you can see that my HTML snippet task is able to generate HTML containing my line count at build time. If I open up my out folder, you can see that there's an out foo/html snippet.json file that contains the value serialized as JSON together with some other metadata that Mill uses to automatically invalidate or cache this thing. And if I wire up HTML snippet into my resources and do foo.run, you'll see that I am now using my application at runtime is using the HTML rendered at build time using a third-party library and some custom logic, and in this case, just printing it out. So again, no one actually wants to render HTML line counts at build time and printing out from the command in the terminal in your application, but it's representative of what many things you have to do in your build that are often pretty bespoke and custom. So in Mill, what's interesting here is twofold. One is you don't see any logic related to caching or parallelism or invalidation here. What you see is pretty vanilla object-oriented code. You have an object that extends a class, you have some methods that call other methods, you have overrides that call super. And just from that, you're able to define a custom build pipeline in the mill build using concepts that you're all already familiar with. The second thing that's interesting is that when I wanted to render HTML in my build, I didn't need to go look for a HTML mill plugin or a mill thymeleaf plugin or some other mill plugin. Uh, I wanted to use thymeleaf. Thymeleaf is a great API and great library for rendering HTML, so I can just use the real thing rather than trying to find some thymeleaf plugin that may be half maintained and last updated 5 years ago on GitHub. So with Mill, working on a build feels just like working in any application code base. You have your libraries available, you have jump to definition available, including in your third-party libraries. You have your autocomplete, you have pop-up documentation, you have type checking. Everything you have, it feels very comfortable working a Mill build in a way that's not the case working in Maven, Gradle, or most other build tools. So that's the programmability angle, where I think Mill is quite cool. Like, it does feel comfortable to anyone who's written any JVM code, Java, Scala, Kotlin in any IDE. And this is much more easy to do than any other build tool that's out there today. So we talked about Mill and some of the interesting things that it can provide, the performance and other performance-related features, the ID support, which is nice, and the ease of programming it. You feel right at home even if you've never used Mill before, things like objects, overrides, and supers. But why doesn't other build tools do this? Like why, Maven and Gradle have been trying to improve their ID support, their performance, and their programmability for 20 years now. Like why are they still not so easy? And I think the answer to that is that Mill relies heavily on this concept of object-oriented builds that, as far as I know, is pretty unique among the build tool solution space and ecosystem. So earlier we discussed how build tools need you to are tools for users to define templated graph computations. And templated graph computations are complex. If you try to define a templated graph computation API, or I try to define a templated graph computation API, it would be a very complicated API. But Mill has one secret here, and the secret sauce is you actually already know how to define templated graph computations via this API known as object-oriented programming. Object-oriented programming with objects, classes, overrides, methods, method calls, and supers, and all that is a perfect fit for these templated graph computations. So when you look at object foo extends Java module, this is an example we saw earlier, it's literally a JVM object extending a class. When you extend a class, what happens? You get all of its methods. These methods pass data from each other, or call each other in one direction and pass data in the other direction through the return values. So when I add a new method, def line count calls all source files. Or when I override resources, call line count, and also call super, you know how this affects the graph. Now, I don't need to teach you what override, super, and method calls do to the method call and data flow graph. You already know how this stuff works. And if I want to template this graph, I can just take my object foo, turn into a class, or in Mill syntax, it's called a trait. I call it trait line count module. And I can inherit it from object foo and object bar, and now I have templated my graph. I have two copies of it. Each object has its own set of methods. Each object has its methods call each other, forming its own graph. And if I want to customize one of these objects, well, you know how that works. You use overrides, and you can override and define your own methods and all that standard stuff. So just by using object-oriented concepts like methods, method calls, classes, and objects, and extends and overrides, Mill lets you template your graphs in a very, very familiar and convenient way. And once you have templated these graphs, Mill can then do all the rest. So Mill can say that, okay, compile and line count don't depend on each other, they can run in parallel. Mill can say that every method has a name, fully qualified depending on the object it lives on, foo.line count, foo.compile, foo.assembly, and we can use these fully qualified names to give each method a unique place on disk to put its JSON metadata, as well as its file outputs, like in the compile.des or assembly.des folder. And Mill can guarantee that these will never collide with each other because every method in the Mill build has a unique fully qualified name, which is how fully qualified names work in any object-oriented language. Mill can do invalidation for you. For example, if you touch the resources folder, which is now called super resources, Mill just does a breadth first search, finds that assembly needs to recompute, finds that compile and line count do not need to recompute, and Mill also knows where to find the cached output for compiler line count, because they're at these standard locations, so Mill can go reuse it. And Mill knows where to find the cached output for assembly, which is again at a standard location, so Mill can go and delete it so he can compute a new output of the assembly. But what's most interesting here is that in this Mill build config on the left, there is no code related to dependency tracking, parallelism, or caching. You don't see depends on clauses like Gradle. You don't see phase specifications like in Maven, or lifecycle hooks like in Maven. You don't see any parallelism things, related things, like you don't see threads, locks, semaphores, executors. You don't see cache reads or cache writes or cache invalidation logic. So Mill generally 99% of the time will just handle all this stuff for you, and all you need to do as a user or as a plugin author even is you write very boring object-oriented code with objects, classes, methods, method calls, and overrides. And that's enough for you to define the graph of the build graph you want to use, and Mill can handle all the rest for you. So if you look at this example from earlier about why build tools are complex and how all the complexities of build tools map onto Gradle's user-facing complexity, Mill actually has to handle all the same things, but Mill squeezes it into a much more familiar package. Like methods have names. We use the method name from the command line, and you're already familiar with how methods have names. You want to customize an existing task, you use an override, and you already know how overrides work, including things like super. What task depends on what? We look at what method calls the task does. What task needs to run in what order? We look at the method calls. How do tasks pass data to each other? They return values from the method calls. So all of these are very familiar to you, and so Mill doesn't skip on these complex areas of complexity, but Mill kind of packages it in a way that is much more familiar to anyone who's ever learned object-oriented programming in the last 10, 20, 30 years of software development. So half of these questions are basically methods, answered by the idea of methods, and half of these questions are answered by the idea of classes and objects. Methods are not just standalone functions, they live on classes and objects. They have fully qualified names, they can be overridden, and so on. So to sum up this object-oriented builds that we talked about, in Mill, builds are built using methods, objects, and classes. In extend, super, override, everything works exactly as you expect. Everything works exactly as IDEs expect, which is why IntelliJ is able to understand Mill build so easily in a way that it can't understand Gradle or Maven builds quite as well. And once you've done all this object-oriented programming and defined your build graph, or templated build graph, Mill can handle all the rest for you most of the time. So you always get good performance because you don't get plugins that forgot to cache things, or you don't have custom tasks that forgot to opt into parallelism. You don't need to clean because you don't have plugins that screw up the cache key computations, which is very common in Maven or Gradle. That's why everyone says you have to Maven clean before you Maven install. And it just makes life easier for everyone. Like you maintaining a build, plugin authors maintaining plugins, it's much easier in Maven or Gradle plugins. And Mill maintainers like me, who have time to do things like selective testing or Chrome profiles, or lots of tooling integrations, and application code, more time to spend on the application code you actually care about. So just talking about tooling integrations, because integrating things with Mill is very easy. We earlier saw how to integrate Thymeleaf with Mill. It's literally 15 lines of code on one slide. We just took the liberty of integrating almost all the common open source projects with Mill. So your Java, Scala, Kotlin, some of Android, all the test suites for these languages, all the linters, auto formatters, code coverage, binary compatibility checkers, publishing destinations, web frameworks. We've actually gone and integrated all these for you built in. And if you want to use something that's not on this list, it's actually very easy for you to integrate yourself, as we saw earlier with how we integrated Thymeleaf. Just pull in the necessary third-party dependency and call it programmatically with full IDE support within your Mill build or within your Mill plugin. So that's the idea of object-oriented builds, which I think is really cool. I haven't seen any other build tool do this, and I've seen a lot of build tools. I've spent 10 years working at various companies on their build tool systems. And I think this is why Mill is able to provide things like the performance, ease of programmability, and IDE support that many other build tools have really struggled with over the past 10, 20 years. So this is the last slide. I guess the long and short of it is, if any of you have had trouble with Maven or Gradle in the past, and if any of you have ever wondered, like, could things be better? Is there a better way? I encourage you to come and give Mill a try. So Mill's a much newer project than Maven or Gradle. It doesn't have the 20-year history that Maven has and doesn't have the 50% of Java market share that Maven or Gradle have. But it has a lot of very interesting ideas behind it, especially this idea of object-oriented builds. And it's not just a theoretically interesting idea, but it actually translates into really concrete user-facing improvements, improve performance, improve ID support, and improve like programmability, all of which are areas that build tools like Maven or Gradle have really struggled with over the past decade. And I think Mill has a chance to really move the needle and bring the experience to the next level of using a build tool. So if you want to look at Mill, the documentation site is mill-build.org. There's example documentation for Java, Scala, and Kotlin. As I promised, like basically everything, testing, linting, packaging, web frameworks, we've integrated them for these three languages. Some experimental Android support. And we have some migration instructions as well if you want to try using Mill on an existing project rather than on a new project, along with automated migration tools that make the migration a bit easier for you. Lastly, all the examples on this docs are downloadable and executable, so you can download this, unpack the zip, and run these commands to try and try out Mill yourself without having to install anything on your laptop or development machine. So I think that's the end of the talk, and I hope you enjoyed the demos and the presentation, and I can now take questions if anyone's interested. Thank you.